Without further ado, let me begin by introducing our first speaker. She comes to us from the Woods Hole Oceanographic Institute, but she actually spends much of her time in some of the remote, most challenging, and poorly understood areas of the Earth, at the edge of major, massive calving glaciers in the Arctic. Not only are these glaciers incredibly difficult to sample, but they're changing constantly. And this is a real action hero or action heroine story of getting scientific information and then making good sense of it. Glaciers really represent ground zero for understanding some of the very critically important interactions between the ocean, the atmosphere, and the cryosphere. How those interact with one another, how they're changing, gives us much needed information about the climate cycle and what's happening underway today. Huge implications for climate change, for sea level rise, and for many other fundamental understandings of the climate system. Dr. Fiamma Straneo is a senior scientist in the Physical Oceanography Division at WHOI, Woods Hole Oceanographic Institute. She received her PhD in Physical Oceanography from the University of Washington, following a degree in physics from the University of Milan. She's co-chair and founder of the Greenland Ice Sheet Ocean Science Network and chair of the Land Ice Team of Studies of Environmental Arctic Change. She was recently honored with the prestigious Sverdrup Lecture by the Ocean Sciences Division of the American Geophysical Union. She teaches and advises students in the joint WHOI-MIT program, and she has been a real not only leader in science, but also focused on communication. And she was honored by selection as a Leopold Leadership Fellow a couple of years ago. So without further ado, please join me in welcoming Dr. Fiamma Straneo.
Thank you, Jane, and especially for the honor of being invited here to present this lecture today. So, building on what we just heard from Jane, we need predictive tools to make decisions about how to deal with climate change, how to deal with many of the changes we're seeing. And our best tools are climate models. And over the last few decades, we've seen amazing improvements in how these models represent the interaction of the ocean, the atmosphere, the cryosphere, the biosphere, the Earth system. What I'm going to show you today, though, is we need to keep improving these models. They're only as good as our knowledge of the Earth system is. And there are areas that are in real need of understanding of processes. And advances in this region, in this area, are really being led by observations. And for the ocean, observations, unfortunately, or fortunately for us who go out to see and enjoy it, usually requires going out on a ship, because the ocean is largely impermeable. You can see the surface of the ocean with remote sensing, but really understanding the deep ocean involves getting measurements with largely in situ instruments. So I'm an oceanographer, but I'm going to start by introducing the Greenland Ice Sheet, which is where I'm doing a lot of work these days at the ocean boundaries. So Greenland is a large ice sheet. It has an area that's about 3 times the size of Texas. The ice is about 1,500 meters thick on average. And you hear anecdotes. If we melt all of Greenland today, sea level will rise by 7 meters. And that's not going to happen anytime soon. But Greenland is changing. And what I'm showing in the plot on the left, in red, what you see is a decrease in the ice thickness over the last decades. This is from GRACE satellites. And so there's a small increase in the center, but there's a net mass loss. So Greenland is shrinking, predominantly around the southeast and western marine margins. And the plot of the right, it's hard for us to wrap our head around what does centimeters a year of ice change mean. So let's talk about sea level rise. Over the last 2 decades, both ice sheets have contributed something on the order of 11 millimeters of global sea level rise. And Greenland has played the lion's role in this. It accounts for roughly 7.5 millimeters of this. And so you can see the 3 plots. The white is Antarctica plus Greenland, and Greenland is the red. And you're all scientists, so there's one thing that you should note about these plots is that the rate of ice loss is increasing. We're not in a nice trend. And so Greenland is losing mass at an increased rate. In fact, it quadrupled its ice loss over just the last 15 years. So why is Greenland losing mass? Well, one way is really intuitive. If you increase air temperatures over the ice sheet, you increase surface melt. And in fact, any time in the summer in Greenland, you're going to see a picture like this, a number of melt ponds. And these melt ponds eventually drain either at the surface or subsurface, and it ends up in the ocean. So this part models are fairly good at reproducing, with some caveats, but at least it's represented in the Earth system models. But there's another way in which Greenland is changing. Like all ice sheets and polar ice caps and glaciers, the ice is moving. So you have ice flow that takes ice from the center of the ice sheet and moves it to the marine margins. And what is shown here is a beautiful representation taken from satellite data that can now reconstruct ice velocity with unprecedented resolution. And I'm not showing the scale, but the blues are the fastest ice flows. They go up to 15 kilometers a year, which for a glacial pace is pretty fast. What you should notice is these ice streams, ice flows, are really gathered in narrow regions, and they terminate in the ocean in some really narrow streams. So the other way in which Greenland has been losing mass is these ice streams have been speeding up and retreating, effectively discharging more ice in the form of icebergs or submarine melt into the ocean. And I'm going to take you to the margins of one of these glaciers. So Helheim Glacier, shown on the left, drains into one big fjord, Sørmelek Fjord, where I seem to be spending more summers than my family would like. But Helheim is one of Greenland's largest glaciers, and it's part of the suite of glaciers that has accelerated over the last few decades. And when we say a glacier accelerate, what we mean is it almost doubled its flow speed. And if you look on the picture of the right, I'm showing 3 images of the terminus of Helheim. So the edge of the glacier is shown in blue. What is to the right is actually ocean. I know it doesn't look like ocean because it's covered in ice, but that's ocean. And this glacier is sitting in about 600 meters of ocean water. And so between 2001 and 2006, it retreated some 5 kilometers, doubled its flow speed, thinned some 200 meters, and it discharged, this glacier alone, in just a few years, enough ice that raised sea level by about 0.5 millimeter. So this is one glacier, and in just a few years. So Helheim is the reason I went to Greenland for the first time, and it was in July 2008. I landed in the town of Tasiilaq in East Greenland, shown here, and this was a really unusual trip for me. Normally I go out, I write a big NSF proposal, I ask for a research vessel, and if I'm lucky enough to get it funded, then I head out with a suite of technicians, a lot of instruments already on the ship, and I know years in advance what I'm going to do. This trip, I actually landed and we didn't know what vessel is maybe too big of a word, what ship or floating, anything we would be using to go and collect the measurements. I also didn't have any funded project. It was really a shoestring budget. But I was there because 2 glaciologists, which are shown with me on the picture in the upper right, had convinced me that we really needed ocean measurements. They're the ones not wearing the foul weather gear, which is something that they would later regret. So the hypothesis that we were testing is we knew from models of ice streams and glaciers that if you perturb a margin of the glacier, such as the one shown, so it comes in and it terminates in the ocean, there's a part that is grounded, meaning sitting on land, and then it fins. And if you perturb this floating part, or you fin it, destroy it, you reduce the buttressing to ice flow. And you can trigger a very nonlinear response in ice flow for a series of ice dynamics. But the point was, what was the trigger? What started the retreat of these glaciers? And one of the ideas that was floating around, this is now a computer simulation, so it's an ocean model. It's one of the state-of-the-art ocean models in a US modeling center, GFDL. And I wanted to show it because I want to show, what amazing advancements we've made in ocean modeling, so you can see the details. And what you're seeing here is sea surface salinity, but it's a good proxy for temperature too at the high latitudes. And in red is salty water, which is water being carried by the Gulf Stream and a suite of currents subsequently around Greenland and into the Nordic seas, into the Arctic. What is in blue-white is fresh water, cold water that is being exported from the Arctic into the lower latitudes. And so if you look at Greenland, especially the part that was changing, southeast and west Greenland, what you see is that it's really protected from the warm waters by a cold band, by these Arctic waters. And so we knew, when we went into the field, we knew that the large-scale ocean had warmed, but we didn't know if these waters actually reached the margins of the glaciers. There were no measurements from the fjords, not a particularly easy place to work in, no real reason unless you want to fish in them, and so there were just no measurements. So that's what we were heading out to see. And eventually we did find a vessel, not the largest, but adequately suited and also within our means. But it was very, it worked very well. And part of why it worked very well is because of the Greenlandic captain who guided us into waters that he had grown up fishing and hunting is. And what we found in surveying this fjord is so we went twice, in July and then September, we found that the lower part of these fjords, this particular one, although we've gone to many others since, was filled with waters from the Atlantic. So in the middle plot, you'll see the temperatures are up to 4 degrees. So these are modified Gulf Stream waters that are reaching the edge of this glacier, which is grounded in 600 meters of water. And above them, you have the Arctic waters. But basically, we demonstrated that these waters had unimpeded access. So that's great, but we want to know about variability, and there were no measurements that we could compare to. And so we did the next best thing. Fast forward 4 years, and we're out with a bigger boat, funded NSF project, and with Danish colleagues. And so what we did is we collected sediment cores. This is Camilla Andersen from the Geological Survey of Denmark. We collected sediment cores, and our hypothesis was very simple. When a glacier retreats, it discharges a lot of icebergs, it carries a lot of sediment into the fjord. And so we expect the sedimentation rate, the deposition rate of the ice-rafted debris to grow. When a glacier advances, fewer icebergs, fewer sediments. And we calibrated the curve we collected with photographs, what available photographs we could find, some dating back to the 1930s, like the ones shown up here. And we reconstructed a time series of what this one particular glacier had been doing for the last 120 years. And what we found is that the period today shown here is sediment deposition rate, or glacier, it's a proxy for glacier calving. This glacier calving was unprecedented over these last 120 years, except for a period in the 1930s, late 1930s, where the ocean was as warm. And so, as often happens in climate, we didn't demonstrate anything, but at least we found that the idea that the ocean was having an impact on the glaciers was supported by this one particular record. So, but what's happening near the glacier? Because I showed you some data, but you would have noticed that we stopped with the small boat, and even with the big boat. At some point, any captain says, okay, I'm done, we're turning around. And it's usually somewhere like this. And this isn't the glacier, this is just an iceberg. We're still some 20 kilometers away from the glacier edge. So how do we get close, measurements close to a glacier? Well, I'm just going to show a brief video taken from the edge of Helheim, and I'd like you to think about a few things. First, the mosquitoes, but these, you never get away from them in Greenland. But the second thing is you're slowly seeing, you can notice how slow these calving events are. The piece that is breaking off is maybe 1 kilometer long, 500, 600 meters deep, and about the same wide. So it's a huge amount of ice, and it's taking its time. This video is several minutes, and the audio isn't playing. But there is an audio. But what you can see if you look in the background, there's a white strip on the back, and so that gives you, we call it the bathtub ring. That is where that glacier was just a few years ago. One of the things that happens when you work with glaciologists, which is very convenient, is they travel in helicopters. And so what we started doing is essentially using helicopters to get to the edge of the glacier, find leads of open water. So now we're flying again on the edge of this glacier. And this is the glacier.
You want me to take the cap off, Jim? Okay.
And deploy probes, patches of open water.
The probe is at 4.
And I show this to give you a sense of scale. So if you looked, you can see the little helicopter over the lead. And now we're going to zoom out. And it gives you a sense of how little we know about these systems. I've been to this fjord and flown in a helicopter maybe 10 times, and maybe we've collected 30 profiles. We're pretty small. You've probably lost sight of the helicopter. This is how little data we have. So what did we find? Well, we found something that surprised us. On the plot on the left in blue, I'm showing what the mid-fjord conditions are. So you have warm water, cold water, a little bit of summer warming at the top. But near the glaciers, the red profile, you actually have seen warmer water in the upper from 200 to 100 meters near the glacier. And on the right, what I'm showing is a section from the glacier mid-fjord, from the glacier to the mouth. And again, if you squint, its temperature, you can see that's warm water that's rising and coming out. And so this is one of the wonderful, amazing things about the climate system. There's so much going on. So what is happening here is you have meltwater that is coming from the surface of this glacier. It's being routed by the glacier system, hydrologic system, to the base. And it's emerging literally as a freshwater tap, hundreds of meters below sea level. This drives huge plumes that upwell, and with them transport vast amounts of heat upward. And the implication here is, yes, you can warm the ocean and drive more melting, but you can also increase surface melt, and through this process of bringing heat up and increasing the turbulence levels that allow the exchange of heat between the ice of the ocean, literally increase melting just by raising air temperatures. And this is one of the things that we didn't know was really going on, hadn't predicted. And again, it's advances being led by observations. Everything I showed you right now, I'm just going to show a few more examples, is very nice because it's two-dimensional. I'm ignoring that the glacier is quite wide. And when you have few observations, it's convenient to do that. But actually, these glaciers obviously very three-dimensional. And so if we want to put this physics in the model, we actually need measurements from the edge of the glaciers. And there are a lot of things going on. What I'm showing here is one of these plumes rising to the surface. It's only maybe 200 meters wide. And this is a glacier that's 5 kilometers wide. So to understand whether they matter to the overall melt, how important they are, which all the models show they are, we need to collect data closer. And so we started working off of nicer glaciers. This is a smaller glacier in West Greenland, smaller boat, but we've taken underwater vehicles such as the one shown. And you can drive this along the glacier face. And this is just a snapshot. The field shown is turbidity, measured through optical backscatter that shows particular content. It's a good proxy for plumes. And what we were able to do here is show that there aren't 100 plumes. There were 2 plumes coming up, one emerging near the surface, one subsurface, and they play an important role in the melting along the glacier face. AUVs are expensive, and the engineers are quite nervous when you put them next to glaciers, where even for the nice ones, we can't get very close because you have huge icebergs coming up from underneath or breaking from the top. So this is another example of a compromised technology. It's jet yak, it's called. It was built for fishermen to go out fishing on lakes. You can take the fishermen out, put a computer in, a lot of sensors, and we can drive it to the edge of the glacier while remaining on a small boat. And now it's driving for one of these muddy plumes, which are very, very fast. And we were able to record some of the first measurements of velocity, temperature. And I give you a sense of scale here. We still have the humans on a little boat, but we have the jet yak really up against the edge of the glacier. And we need these measurements because the scales, temporal, spatial scales, involved with melting at the edge of glacier range essentially from molecular all the way to the fjord scale. And there's no computer simulation right now or lab simulation that can cover all of them. So I'm going to end here. My summary is really a selection of snapshots of people. It's the glaciologists that brought me to Greenland, the paleoceanographers that allowed us to reconstruct history from these places where we had no ocean measurements, the helicopter operations, the underwater vehicle operations, the jet yak, the surface autonomous vehicle. And so my point here is that, first of all, we need these observations to improve our models. We need to work with the modeling community, which we're doing. But in the end, it's science relies on people. And in this case, it's a very interdisciplinary problem. It's a very complex problem. We've really been able to make progress thanks to all of these different fields coming together and working together. And it's been a wonderful community. And I think it's a good representation of how we should do climate science in collaboration across nations and across disciplines and across tools. Thank you very much.
Thanks, Fiamma. Thanks for giving us a sense of some of the real challenges of acquiring the data that we often take for granted in many of the big models and simulations and results that we see. This is the opportunity now for you in the audience to ask questions of Fiamma. We have microphones that are in the aisles. Because this is being recorded, we need you to please go to one of the microphones, pose a question to Fiamma, tell us who you are, and then ask your question. And we'll do that for about 10 minutes or so, and then we'll move to our next speaker. So please, our first speaker, first questioner.
Is this on now?
Yes.
Yes. Hi, I'm Bonnie McKay from Rutgers. Fiamma, thank you so much. That was really inspiring. And I appreciate the, how upfront and personal you made the efforts to measure to know. That was brilliantly done, and I'm sure Ellen Alder would appreciate this. I have a question about the community that you emphasized at the end. And I would imagine that you also learned a good bit from local people, and that local ecological knowledge or experience with the glaciers was important. I'd like to hear more about that.
Yes, I mean, one thing that I should say is I would not have been able, and I can speak for many of my colleagues, to make these measurements without the local knowledge. These fjords are uncharted. We don't really know what we're doing. And so in that sense, it's been really useful. From a scientific perspective, we have created these networks, which are grassroots efforts. And we've really asked the local, especially the local scientists. There are scientists all around the Arctic. In my case, I work with the Greenlanders. What is the information that we can provide? Because now we are really intensively studying these systems. And so we're now working with marine mammals experts. I didn't show, we have a lot of moored instrumentation, and we put acoustic receivers to study the patterns of whales, and we've tagged seals. So I hope that as part of, we went to Greenland with the idea of studying the physical system, but we're really putting together a picture of what the biological and chemistry that's going on is happening. And we're working with the local fisheries and so on. And it's been a really rewarding experience. Thank you.
Fiamma, I think you may have experienced the same thing I did in Greenland, which was deep local knowledge from the people who live there, not just the scientists that study the place. And that's adding significant additional value to what the scientists are finding. And it's a really interesting combination of traditional knowledge with scientific knowledge.
That's right. Yes, absolutely.
Let's go over here.
I'm Granger Morgan from Carnegie Mellon. Could you talk to us about the current state of understanding of the role played by surface meltwater lubricating the underside of glaciers and hence accelerating the flow rates?
Yes. So I'd say that is not necessarily a competing hypothesis. So as we increase surface melt, there's more drainage to the base of these glaciers, and it affects effectively the frictional controls. I'm not a glaciologist, but I hang around them a lot recently. And so my understanding of the state of knowledge now is that lubrication is still an important player, especially in some of the seasonal speed up. But it is also not the only player. We cannot explain a lot of the changes just based on increases in surface melt and lubrication. It is a very active field of modeling. And if you think that measuring the edge of the glaciers is difficult, measuring the sediment and the water content and the channels under the glaciers, that's much worse. So if you need a challenge, that's a good field to go in.
Hi.
Yes, please.
Oh, you may have partly answered this question. I'm Roy Radner. But we read a lot of that estimates of climate change are that it's accelerating. Each new set of studies seems to talk about things happening faster than we thought. How does your research bear upon that question?
It's unfortunately true. We are not keeping up with the changes we are seeing. So even this area of research is very much in reactive mode. We see something unexpected happening. All of the changes that I talked about, especially the dynamic ones, were not predicted by models. So the scientific community, and then it's in reactive mode. We literally rush to a site after something has happened and try to reconstruct it. It would be easier if we had a lot of measurements in place now, so at least we're not in reactive mode all the time. So if any of you have control of how many measurements we can make, we need more data.
We have time for 2 more very quick questions and short answers.
Fiona, you made a great case for the necessity of being there in situ, but you must have an incredibly short window in which you can be there. Can you say something about the large window of the year when you probably can't get into the field, and what are the prospects for making measurements by some other means when you can't get out there in little boats and even bigger ships?
Thank you. This is a very good question. I didn't have time to show it because Jane only gave me 20 minutes, but actually 90% of my work involves anchoring instruments and leaving them in the fjord. So we've been monitoring this particular system since 2008. We leave instruments behind. Even that is incredibly challenging. The icebergs are several hundred meters deep, but we want to measure that part of the water column. So we're finding tricks. We've lost lots of equipment to icebergs. We're finding tricks, acoustic measurements, integrated measurements to try and measure the heat content without actually having an instrument there. In Greenland, the window of summer is a couple of months a year, and the winter is the other 10 months. And it's only by leaving instruments behind that we can sample that, and we should all be skeptical of just summer snapshots.
That last question was posed by Marcia McNutt for those of you who are joining us remotely. Our final question, Chris?
Thanks. Chris Field, Carnegie Science. Wonderful presentation. We tend to think about Antarctica, especially West Antarctica, as being mainly ground surface below sea level and Greenland being above sea level. But you talked about glaciers that are grounded below sea level. Can you say a few more words about this below sea level, above sea level business?
Yes. So that's a very good question. And I talked about Greenland, well, because I worked there, I guess, but it's also a question of timescale. So the processes I talked about involve having an interface between the ocean and the ice. And so many of the fast-flowing systems that I showed in Greenland are actually below sea level. Some of these narrow troughs go all the way to the middle of the ice sheet. But it is true that eventually a lot of the glaciers in Greenland will retreat above land. Not all of them, but a lot of them, which means the dynamic ice loss from Greenland will slow down. West Antarctica, which is why it's so much in the news, even though over longer time scales, the amount of ice that is submerged is much, much greater. And so we can expect much larger changes over much larger time scales from Antarctica because the contact between the ocean and the ice will persist for much, much longer.
So thank you so much, Dr. Straneo. We really appreciate your getting us underway with that. Please join me in thanking her.
Thank you.